Okay, now comes very important stage in the system, the filters. If you read the names, the first one is USB filter. It stands for upper sideband filter. And the second one is LSB filter, stands for lower sideband filter. USB filter will simply allow only the upper sideband to come at the output side, and it will block the lower sideband. So the output of USB filter in the upper branch of the system will be from FC to FC plus FM1, which is the upper sideband of the first modulated signal. And similarly, the lower sideband filter will only allow the lower sideband to come at the output side, and hence the output of the lower sideband will be from FC minus FM2 to FC. And you can see that finally we are going to add the two outputs. So my final output which is added, I'm calling it ISB, independent sideband signal. And if you observe carefully, because there is no overlapping in the frequency components, the upper signal contains frequencies from FC up to FC plus FM1, and the lower signal contains frequencies from FC to FC minus FM2 on the lower side. When you add the signal, linear addition will give you the overall frequencies starting from FC minus FM2 up to FC plus FM1. So you can see that upper sideband will correspond to, I'll call it upper sideband 1, it will correspond to the first modulating signal, and the lower sideband will correspond to the second modulating signal, I'll call it LSB2. The total bandwidth of this signal will be nothing but FC plus FM1 minus of FC minus FM2, so that will come out to be FM1 plus FM2. So let's say if we have a case where FM1 and FM2 are exactly same, equal to FM, then my bandwidth will turn out to be twice FM, which is exactly same as the bandwidth of DSB signal coming out from one modulating signal. So let us now try to understand what have we achieved and what exactly we mean by independent sideband transmission. So as you can see, the word independent sideband simply means that we still have the two sidebands present around the carrier frequency, single same carrier frequency, but both the sidebands are independent from each other because they do not contain the same information anymore. The upper sideband contains the information of the first modulating signal, and the lower sideband contains the information of the second modulating signal, and hence they are called independent sidebands. Now, what is the advantage of doing this independent sideband transmission? The very first advantage is that I'm using the same carrier frequency. I do not require two different carrier frequencies to send the two different modulating signals. I'm using the same carrier frequency, and hence on the same channel, on the same transmission channel, I can transmit two different modulating signals which are independent of each other. If I had to do it using any conventional amplitude modulation process, it will not be possible because M1T itself will require the bandwidth of twice FM, and so will M2T. And both the sides of FC will be occupied by upper sideband and lower sideband of the same signal, either M1T or M2T. So somehow I first had to make space for one of the two sidebands of the other signal to be placed around the carrier signal, and hence we remove the lower sideband in the first channel and upper sideband in the second channel, and we add the signals. So by doing this, you get a double sideband signal with the bandwidth twice FM, but in the same bandwidth of twice FM and with the same carrier. That is something which is more important. Using the same carrier signal, we are transmitting two different information signals. On the receiver side, all receiver has to do is tune itself to the carrier frequency FC and have the bandwidth equal to twice FM. In that case, it will receive both the signals. The entire modulated signal will contain sidebands coming from both the modulating signals. Now let us say the receiver wants to demodulate only M1T. In that case, the receiver will use a filter which will be upper sideband filter, again the similar USB filter. It will extract the upper sideband, remove the lower sideband. Now receiver will simply treat this as a single sideband signal and use any SSB receiver that we have discussed, any SSB demodulation system to demodulate M1. On the other hand, if the receiver wants to demodulate M2T, then it can use LSB filter, first extract the lower sideband and use any SSB demodulation system to demodulate M2T. It can do this simultaneously in two different branches and demodulate both M1T and M2T at the same time. So in many applications where we have one carrier signal, we want to use only one carrier signal, but we want to transmit different information signals which are independent of each other, but there might be some kind of relevance between them. That totally depends upon the application. So in such cases, we may use independent sideband transmission. One drawback of this whole system would be that whichever receiver you have which is tuned to the carrier frequency can easily receive both the sidebands, and hence it will have information signal coming from both the sources, both the modulating signals. You can't make receiver to receive only upper sideband and demodulate only M1T, or receive only lower sideband and demodulate only M2T. So only when you are fine with receiver receiving all the signals that you have attached, both the modulating signals that you have attached, you can use independent sideband transmission.